Hi guys, in this session we're going to have another theorem. Besides all the theorem we saw about taking the limits of the sequences, such as L'Hopital theorem, main limit theorem, continuous function theorem for the sequences, we still have some other tools we can use directly to solve some common type of sequence limit problems. Of course, these sequence limits, these features, these rules can be proved, okay, using the all other techniques, but we're just gonna keep, we're gonna put them aside, okay, so that we can use directly besides the all other tools, okay, to be able to solve the sequence problems. Let's look at what they are. The first one, we already know, okay, since I solved this one as an example in L'Hopital rule, which is 0. Since look at it, if n goes infinite, ln n goes infinite, infinite over infinite, you can just apply L'Hopital rule to find out if it is 0. The second one is about square root, but this time radical n, which is 1. Another technique we have, but we're not going to prove it, we can use to take this type of limit. If you remember from Calc 1, you can use the ln type of technique to take the limit of the square root. But that's not our job today. Another rule is about this one. This is so obvious. When n goes infinite, 1 over n goes 0, right? And then x over 0 is going to be 1. But this applies for the positive x values. The fourth rule, I already shared this with you before, 0 for the values they are less than 1. The fifth one, a little bit interesting, 1 over x over n, x over n to the n, which is equal e to the x. And this rule applies for any x. And the sixth rule is about this one, x to the n factorial, which is 0. And then again, we can use this rule for any x, okay? The fifth one and the sixth one is a little bit right interesting and weird, but the fifth one can be solved using the ln type of features, okay, in the limit problems, but the sixth one should be solved using the sandwich theorem, since I didn't show what the sandwich theorem for the sequences. That's why I'm not going to get into the details of that one. Let's look at some examples. The first example is about using the second or the third rule. I don't remember the number of it. Look at this one. What would you do if you had such a thing, right? Yes, you would use the continuous. You might think you can use the continuous function theorem, but look at that. Since you have the n radical radical n as a root, so you cannot use this continuous theorem, since you need to be able to switch the function. But I can't do that in this case. What am I gonna do? I'm gonna be using one of these tools. If you look at the second rule, it says something about it, but before using that one, I will try to use, sorry, that's my bad, let me fix it. I will try to use some algebraic feature of the square root, guys. This is still n, and I have n here, but I can move this tree right on the top of whole expression. Now I'm ready to use one of the continuous function theorem together with the rule I gave it to you. So I can switch the limit by the function. And this is the function, right? X cubed. And look at that. Do I know what that limit is? Yes, I know that. This is 1. 1 cubed is gonna be equal 1. You see? I'm not just using, right, the rule itself. I'm combining the rule with some algebraic techniques around. That's what you should do, guys. Okay? That's why you need to be good at algebra. The second example is this one. Limit when n goes infinite, n 7n, right? We can say the same thing. I can't just use the continuous function theorem for this problem, but I can use some algebraic technique before I use these rules. Can I separate these terms in this way? Yes, of course. And mainly limit theorem gives me some idea, right? Since I can separate these two terms, then I can take the limit. But I see something else. This is equal this one, and then I already know what that limit is since I just solved, right, in previous example. This goes 1, and then this part goes where? You remember from the third rule I gave it to you. Since when n goes infinite, this will go 0. 7 to the 0 will go 1. So 1 times 1, which is 1. Another example. Limit when n goes infinite, 1 minus 3 over n to the n. Just pause your video and then think about it, okay? What rule would you use for this limit? I would use, right, the rule 5, since it is direct application of, right, that part. You can just call it the E rule. I don't know, since I have the E number on the right hand side. Since look at that, I have what here? A number, which we called as an X, right? This is my X number, you see? This is X. X here equal -3, so the result is going to be directly to the -3. That's it. But look at this example, which is similar to this one, but there's a special thing here. You need to see that. N minus 4 over n to the n. So I have the power of n, and then I have some other things right around. But I'm thinking I can use the same rule, right? But it is not equal to the same structure. You need to have the same form inside to be able to use that rule. But if you look at, right, the sequence itself, you don't have the same thing. But can I do this one before I use the rule, since I need to have the right 1 plus x to the x over n to the n structure. So I can separate, right, in this way. I can factor it out to have that form in the rule. Now look at that. Now I have 1 minus 4 over n to the n. If you look at carefully, right, this is same form in the given rule. And then now what I have right here, this is the number -4, and I can just write the result e to the negative x, which is, sorry, e to the x, so e to the -4, right? This is going to be the result. Okay, guys, this is the end of the sequence section, and then we learned everything about how to find out the convergence of the sequences. You will see in the series section, okay, series question is gonna be all about the sequence convergence. That's why, okay, we're gonna need to use all these features, all these rules, all these theorems, okay, when we solve the series problems. You are gonna see, okay, closely when we cover the series topics. Okay, see you guys.